So welcome to the afternoon session. It was very nice this morning. I enjoyed quite a lot of all the talks, and now we go with two more talks. One by Valentin. It's very difficult to Skoutnev is okay?
Skoutnev, yes.
Okay, Valentin Skoutnev. He just finished the PhD at Princeton University, and now it's starting a postdoc very recently at Columbia University as a THAA fellow. It's theoretical high energy physics, right?
The astrophysics, yeah.
And physics and astrophysics, correct. So, and Valentin will speak about the Dynamos, small scale and perhaps large scale operating in the stable layer below the convection zone. So Valentin, please take it away.
Okay, thank you. Thank you for the introduction, Gustavo. Okay. Okay, so can everyone see my slides?
Yes, yes.
Okay, okay, cool. I will try to hide floating. Okay, there we go. Okay, cool. Yeah, so my talk is going to be on the fundamentals of dynamos in strongly stratified turbulence. This is basically the result of my PhD with my advisor, Amitava Bhattacharjee at Princeton, and this is in collaboration with Jonathan Squire, who's at the University of Otago in New Zealand. Before I start, just given the nature of my understanding of this workshop, I just thought it would be good to give, I guess, my perspective of where I think this research fits into, I guess, the broader philosophy of fluid dynamics, of this particular problem of trying to understand radiative zone dynamos. So typically, you can think of them, people think of these complicated systems as kind of breaking them down to different scales. At large scales, you have things like boundary conditions and spherical curvature effects and driving. And then if you go down to smaller scales, you have these mesoscales where rotation and stratification and some instabilities are important. And then small scales where you care about things like viscosity and resistivity, and as well as some instabilities that also operate on small scales. The talk today is going to be on small scale and large scale dynamos. The small scale dynamo generally cares about the anisotropy of the turbulence. So it's going to operate between the mesoscales and the small scales, just broadly speaking. And as many of you know, why we haven't really solved this problem is the large scale dynamo really couples everything. It cares about boundary conditions, it cares about spherical effects, but also cares about rotation, stratification. It cares about things like the resistive scale and something like alpha quenching, how quickly helicity is dissipated at small scales. That's something that is important. A high magnetic Reynolds number that's hard to capture in global simulations. And so there's this top-down versus bottom-up approach. As I view it, the global simulations put most of the resolution trying to understand the effect of these large scales, but they sacrifice a lot of physics in the mesoscales and the small scales. While this talk is going to be more of this bottom-up approach where most of the resolution and thought is put into the mesoscales and the small scales, but I lose a lot of realism kind of connecting to large-scale things like boundary conditions and curvature and things like that. Okay, so with that in mind, the motivating question behind this approach and this research is what dynamos can asymptotically operate in the conditions of a stellar radiative zone. And this asymptotic word is the key word here, because simulations can only go so far in dimensionless parameter space. And when I started this project, I found that surprisingly little is known about dynamos in radiative zones from this bottom-up approach. So this includes the effect of strong stable stratification, the effect of a low thermal Prandtl number. This is very relevant in young stars where composition effects, the stratification from composition is not yet important. And then also the role of a mean shear from radial differential rotation combined with stable stratification. Okay, so the approach is basically to very thoroughly examine a local turbulent patch of a stellar radiative zone. So whenever I talk about a box or turbulence, you kind of think of it as taking a chunk out of a turbulent sphere and trying to understand what's happening on the meso and the small scales primarily. Okay, And before I actually jump into the work, I want to go through some basic terminology, make sure everyone's on the same page. There's two types of differential rotation that we'll be talking about. The first is radial differential rotation. So this is usually stable due to stratification. This is rotation on shells, so rotation is a function of radius. And this usually kind of provides a roughly background mean flow to where the dynamo might operate. And then something like, latitudinal differential rotation is kind of focusing on an equipotential surface and having differential rotation that's a function of the polar angle. And because this is on an equipotential surface, this is easily unstable to horizontal shear instabilities that will drive a lot of the small scale turbulence mentally as a physical motivation inside of a radiative zone. And this has kind of been shown to be pretty effective in a lot of work by Laura Cope and Pascal and others. I keep mentioning stable stratification for just those of you who do not work in this field. The idea is that in a stably stratified region like a radiative zone, you can really zoom in locally on some region, and there's some prescribed background density, pressure, and temperature profile given by the stellar evolution equations. You imagine perturbing a fluid element subsonically, and if you perturb it, it's going to adiabatically expand. It's going to, as it expands, it maintains pressure equilibrium, and assuming that this expansion is not modified by thermal effects, the density is going to be different than the background density profile, which is not at the adiabatic rate. So this leads to some restoring buoyancy force, and it turns out that basically the ideal motion is just oscillations with this Bernoulli frequency. So it's kind of like a linearization of motions around a background equilibrium. And the equations that I'm going to use and are generally used to study the perturbations on top of the background in a radiative zone are the Boussinesq equations. And they're you can show that rigorously. They're their expansion of the compressible fluid equations, with the small parameter being the subsonic velocity or the local kind of height relative to the scale height. And they're basically the Navier-Stokes equation, but it's coupled in the vertical direction to the buoyancy force, this theta variable that I label, which is proportional to the temperature fluctuations. And the strength of the coupling is set by the Boussinesq frequency that I just mentioned. And this coupling is only in the vertical direction. So you imagine that your turbulence is basically free to be Navier-Stokes in the horizontal direction, but it's restrained in the vertical direction. And the other two important parameters are the viscosity and the thermal diffusivity. And so these are the equations I'm going to be working with. Okay, so quite literally, I'm going to present this bottom-up approach of creating models of increasing complexity. So the talk has kind of three parts. Given the 30-minute constraint, I can only go so far into each one. So I'm going to try to give you the kind of the most important ideas in each one of these. So basically, I'm going to start with just examining hydrodynamic stably stratified turbulence and the possibility of what happens with the thermal Prandtl number is really low. And then do the mental experiment of then adding the possibility of magnetic fields. So this could be a very turbulent medium, and it could possibly drive a small scale dynamo. So you'll be able to generate small scale magnetic fields inside the stably stratified turbulence. And then the next step would be to add a mean shear on top of this turbulence, and this would be modeling something like radial differential rotation in a star, and then examining at least at the scale available, generation of large scale mean fields that are larger than the forcing eddy scale of the stably stratified turbulence. Okay, so part one, hydrodynamic stably stratified turbulence. The way I like to think of it is, imagine that you have a stably stratified fluid and you start forcing it with some horizontal length and horizontal velocity scales, presumably from some external instability given to you from the global picture. This system is fully characterized by three dimensionless parameters: the Reynolds number, this important number known as the Froude number, which goes as 1 over the Brundt-Rosal frequency, and also the thermal Prandtl number, the ratio of the viscosity to the thermal diffusivity. If you estimate these numbers in the Tachocline, given the nature of this workshop, I'm going to focus on numbers in the sun. Basically, the Reynolds number is order 10 to the 13, the Froude number is order 10 to the minus 4, and the thermal Prandtl number is about 10 to the minus 6. And I'm going to use these numbers to make estimates for different scales of the turbulence. And we want to understand just from the hydrodynamically, what are the emergent outer vertical scales, and what is the scale by scale anisotropic energy cascade from these kind of given large horizontal outer scales. The regime there, I think there are two regimes in stably stratified turbulence, depending on the thermal Prandtl number. And the most studied one is this geophysical regime where the Prandtl number is order 1, so the viscous and the thermal scales are roughly the same size. This is relevant to Earth's atmospheres and oceans. And it's been worked out roughly in the last 15, 20 years or so. And people have found that if you imagine thinking about the largest eddy in your turbulence, it's going to have some horizontal scales, and the vertical scales end up scaling with the Froude number times your horizontal scales. So the Froude number was 10 to the minus 4. That means if you excite some turbulence with some horizontal scale in the Tachocline, the vertical scale of the fluctuations is going to be about 10,000 times smaller. With that, you can calculate what is kind of a vertical Reynolds number. It's quantifying the strength of the viscosity on the very narrow vertical scales. And you want this to be turbulent, so you don't want viscosity to be important. So if you estimate this vertical Reynolds number, it's the Reynolds number times the Froude number squared, just plugging in UV and LV. And this is a very important number known as the buoyancy Reynolds number. And this is generally large in Earth's oceans and atmosphere. And it's about 10 to the 5, 10 to the 6 in the Tachocline. So this telling us that the turbulence is, it is turbulence, not viscously kind of constrained in the vertical direction. You can do the same thing for the effect of thermal diffusivity on these very, very narrow vertical eddies. So this is known as the vertical Peclet number. And because the Prandtl number is order 1, this number is also going to be relatively large in this regime. However, if you take the thought experiment of now keeping everything constant, so you maintain your same forcing, you maintain the same stratification, and you just decrease your thermal Prandtl number by increasing the thermal diffusivity, at some point, the thermal timescale across your very narrow vertical scale is going to be comparable to the eddy turnover time. And this is when this turbulent vertical Peclet number becomes order 1. And so there's been many numerical studies that kind of found transitions to occur when this turbulent Peclet number becomes order 1. And if you just rewrite this criterion, this is basically when the Prandtl number is 1 over your buoyancy Reynolds number. And if we estimate this product in the Tachocline, just order of magnitude, it's very close to order 1, maybe possibly smaller. So that's telling us that thermal effects might actually be important in modifying the stably stratified hydrodynamic turbulence in the Tachocline. I'm not going to go into more details about this thermally diffusive regime. There's been a lot of work on this in the last few years. And very recently, I came up with a theory of my own by extending the ideas of critical balance from MHD to this regime. And if you're interested, I recommend checking out my paper. But it turns out, according to this critical balance predictions, that the scalings are actually very similar in this thermally diffusive regime if you simply replace the Froude number by a modified Froude number. That's just given by this complicated expression, but it comes from a bunch of algebra. So we can just think about the geophysical regime, but if we ever want to consider turbulence in the thermally diffusive regime, I argue that you just have to replace the Froude number. And this theory is nicely self-consistent because you have a smooth transition across the threshold here when the turbulent vertical Peclet number is order 1. So that's kind of a summary of the hydrodynamic stably stratified turbulence. And before I move on to the dynamo, I think it's important to try to understand this turbulence from a spectral perspective. So the way to there's I guess 2 ways to look at it. One is to look at it in wave number space. One is to look at it physically. So if we take a look on the right here, if you imagine breaking down the turbulence as a function of the horizontal size of the eddies, hydrodynamic turbulence has this nice property that if it's anisotropic at large scales, it's going to progressively become more and more isotropic at smaller scales. And the transition between the two is known as the Asimov scale. So you have an isotropic cascade followed by a isotropic cascade down to the Kolmogorov scales. So that's kind of in thinking about in physical length scales. If you think about it in spectral space, so imagine the energy spectrum of the velocity field as a function of the perpendicular wave number. You have some large region of some large cascade size that's very anisotropic between your low K forcing scale and the Osmedov scale. You could show that the anisotropy is quantified by the scaling law using critical balance. But I think the main takeaway is that the size of this you can estimate as the Froude number to the power of -3/2, again, coming from some of the scaling arguments. And this number is actually quite large in the Tachocline. So if you take the Froude number of 10 to the -4, the scale separation is about 10 to the 6. So you have a factor of 1,000,000 between your driving, like if you have a horizontal fluctuation in Tachocline, to the scales at which it becomes isotropic turbulence. And then from the scales, from these Osmedov scales where the turbulence is isotropic, all the way down to the viscous scales, the size of this portion of the cascade is given by the buoyancy Reynolds number to the power of 3/4. And that's kind of intuitively because the buoyancy Reynolds number is quantifying, it's kind of like the local Reynolds number of just this cascade, as if the Osmedov scale is your outer forcing scale. And the size of this is about 10,000. So you have 1,000,000 scale separation between your forcing scale and your Osmedov scale, and then a factor of 10,000 between your Osmedov scale and your smallest viscous scales in the Tachocline, assuming it was all hydrodynamic. Okay, so to summarize, it turns out that in stably stratified turbulence, there are actually only two important dimensionless parameters: the buoyancy Reynolds number and the thermal Prandtl number, which control stably stratified turbulence. And a transition probably occurs at when the product of them is order 1. And according to my critical balance theory arguments, the transition between the two is basically a change in this modified Froude number between these two regimes. Okay, so now for the second part, assuming this is the theory for the background hydrodynamic turbulence, we can try to make some arguments about when a small scale dynamo could operate in this type of highly anisotropic turbulence. And to do that, you basically assume the MHD approximation. So to couple that with the Busnesque approximation, you just add the induction equation and the Lorenz term in the momentum equation. And we want to understand what dimensionless parameter regime is unstable to the small scale dynamo. So our new parameter is the magnetic Prandtl number, capturing the effect of resistivity, and this is typically smallish in main sequence stars. Okay. There's several ways to present this, but I think the easiest way is to give kind of an anti-dynamo argument in spectral space. And the intuitions as so let's just work in, again, the spectral space of the perpendicular wave numbers. In this isotropic portion of the cascade, the parallel and the perpendicular fluctuations of the velocity field relative to gravity are going to be order 1, right? Because it's just isotropic turbulence. You imagine this is just the standard dynamo, standard small scale dynamo. However, in the anisotropic portion of the cascade, there's going to be an inefficient dynamo because the parallel to the perpendicular fluctuations in the turbulence, if you estimate this using critical balance, has some scaling that goes as the perpendicular wave number over the Osmedov wave number squared. So this becomes very quickly very small as you move from the Osmedov scales to larger and larger horizontal scales, which are become much more anisotropic. And asymptotically, the flow becomes a 2-component flow that kind of depends on all three dimensions. And this is a well-known anti-dynamo theorem. And so this suggests that basically the dynamo here is very inefficient. So if you have very, very small UZ or U parallel velocity, it's not really going to give you magnetic field amplification. And so this suggests that the dynamo requires a large scale separation between the Osmedov wave number and the resistive wave number, wherever it is. And if you go through the scalings, you could show that their ratio goes as PM times this buoyancy Reynolds number, which is kind of like the effective Reynolds number, as I discussed, and suggests a small scale dynamo instability criterion for the product of these two to be larger than some critical value that depends on the magnetic Prandtl number. And this is fully analogous to isotropic turbulence, where in order for the small scale dynamo to operate, the magnetic Reynolds number needs to be larger than some critical value, order 100 or 50 or so. And that depends on the magnetic Reynolds number. Here we're just replacing the buoyancy Reynolds number with the magnetic Reynolds number. Okay. So the scalings are nice in theory, but we can try to test this with DNS. And so what we did was very simple experiments. We had 3D periodic boxes, just Snoopy, which solves the MHD Boost-Nest equations. We forced kind of near the box scale, about a third of the box scale with time correlated body forcing. So just simulating turbulence at large scales, and just put in a very weak mean field and just measured the dynamo growth rate. So after a very brief transient phase, as you increase the stratification, you can see that the growth rate from blue to orange to green slowly decreases. And so this is kind of snapshots at the end of a run of different stratifications of the different fields. So the temperature field here, you can see in the unstratified case is just a passive scalar. Stratified case, you see very anisotropic turbulence that has some vertical scale height. And then if you increase the stratification like way too much, you basically have viscous coupling and the turbulence kind of disappears. And that's intuitively what you would expect. The dynamo becomes less efficient until it actually fully shuts off, because your turbulence is basically quasi-2D, quasi-2 component. And so you could kind of, because these are very cheap, you can just scan the Reynolds number versus the inverse Froude number plane and kind of confirm. We end up confirming the scaling predictions. So this is just plotting the dynamo growth rate for each one of these parameters. So each one of these crosses is a simulation with a measured growth rate, right? So at low stratification or no stratification, the contours are just horizontal. The dynamo growth rate only depends on the Reynolds number, the Reynolds number, because it's isotropic turbulence. But for any Reynolds number, if you increase the stratification, eventually the dynamo will shut off. It doesn't matter what Reynolds number you choose. At some low enough Froude number, the dynamo will shut off. And so you can see that the contours start to align with this very close to this Froude number to the power -2 scaling. And so this is exactly the criterion that I was arguing for earlier. If you just rewrite this, this is requiring that this buoyancy Reynolds number needs to be larger than some constant, which we're able to measure from the simulations. For PM equals 1, it's order 3. And so you might generally think that the critical value for the dynamo is having RB order larger than something order 10 or so. Okay, and as I mentioned, the keyword is asymptotics. If we believe our scaling prediction for the small scale dynamo, we could extend this Reynolds number versus inverse Froude number plane to realistic stellar parameter regimes. So the Reynolds number in the Tachocline is order 10 to the 12, 10 to the 13. So that's over here. And then the Froude number is about 10 to the -3 to 10 to -4. So the Tachocline sits somewhere in this region here. And then if we plot the small scale dynamo criterion, you can see that the Tachocline actually is turbulent enough, and the magnetic Reynolds number is not low enough to actually suppress the dynamo. And so this predicts that asymptotically there should be a small scale dynamo operating in the hydrodynamic turbulence of presumably the Tachocline. But it's actually surprisingly like not too far away from being stable. So this means that in other stars where the stratification might be stronger, or the driving force of that's driving the turbulence is weaker, presumably it actually might be stable to the small scale dynamo. And so with that, I just want to note that actually hydrodynamically Earth's atmosphere is very close to the Tachocline. So if you were to fly a plane through it, you would roughly experience the same amount of turbulence, perhaps. Okay, so to summarize this part, this magnetic buoyancy Reynolds number is what I predict to be the new dynamo criterion in stably stratified turbulence. Again, thinking about the geophysical regime. And if you extend the scalings to typical parameters in the sun, it seems plausible to have a small scale dynamo, but it's not super obvious that it would have been ahead of time. This critical value is order 10, and this PMRB is order 10 to the 3, depending on what you estimate in the solar radiance zone. And then I don't go into this, but a low thermal Prandtl number, which is true of a sun, actually makes the dynamo more efficient. And Prandtl number can even be lower in some other stars. So you also have to take note of that if you want to do a more realistic estimate. Okay, so so now we've discussed hydrodynamic turbulence, we've added small scale magnetic fields, and now let's add, so we've moved up from kind of small and mesoscales, and now I'm going to kind of take a reach and try to do a little bit of a dynamo, like a large scale dynamo, in stably stratified turbulence and shear. And so the way we're going to do that is to now impose shear onto the box and see if we can observe the generation of a large scale field that's larger than the turbulence scale inside this box. And I'm going to present one type of dynamo mechanism, but I think this is a part of a much broader picture of how does stable stratification affect known large-scale dynamo mechanisms. So a lot of mean field theory kind of is based on assumptions of more or less isotropic turbulence, but as I've shown in radiative dynamos, in radiative zones, the turbulence is highly anisotropic. And so it's not immediately obvious that you can just extend mean field theory to radiative zones. So I think that this question needs a lot more study. And so the new parameter, if you add shear to a box, is this new dimensionless parameter. The shear parameter is the shear divided by the eddy turnover frequency. And this is actually quite large in the Tachocline. And this is simply because the radial differential rotation is stronger than the latitudinal differential rotation. And that's driving the turbulence. Okay, so the coordinates of the shearing box are basically aligning the shearing direction with the direction of gravity. That's because you have radial differential rotation. So this box, in shearing boxes, you align the x direction with the direction of shear, and the flow due to radial differential rotation is in the toroidal direction, which is the y direction in the box. Gravity is also in the shear direction, so it's in the x direction. And we're going to want to study the generation of a axisymmetric toroidal field that varies with something like the polar angle. And so in the box coordinates, that's a by directed field that's only a function of the z coordinate, the polar coordinate. And so if we can observe a by field that only varies as a function of the z direction, that's kind of like locally, you could think of this box being on the equator or something as a toroidal field, a mean axisymmetric toroidal field that's varying as a function of the polar angle. And this is basically as well as you can do with the kind of bottom-up approach. Okay, so the benefit is that we can put a bunch of resolution into this box, but we lose kind of the realistic effects of curvature and boundary conditions and stuff. But anyway, so it is. So we extended. I'm not going to go into detail of this. Is not super interesting, but we extended the theory of SOCA to include the Boost-Ness equations. So basically including the effect of stable stratification perturbatively. It's not very practically interesting, but basically in mean field theory, all the coefficients get these corrections due to the presence of the Brent-Massala frequency, and they generally suppress the dynamo, as you might expect. And so I'm going to focus not on alpha effects, so just on the magnetic shear current effect. And the way this works is in the presence of a shear. If you have a radial field or a BX field, it's going to be sheared into a toroidal field or a BY field. In order to close the dynamo loop, the argument is that the radial field can be rebuilt by this anisotropic turbulent resistivity of acting on your toroidal field or your BY field. And so the dispersion is shown here, and this can work only if this eta yx term is actually negative. And so different closures find that this coefficient can become negative in the presence of non-helical magnetic fluctuations, i.e. from a small scale dynamo. This kind of has been a matter of debate, but it seems to work in simulations. There are some corrections, but I'm just basically going to jump to using simulations to test this. So again, we use the Snoopy code. We set up this box with the shear, and I'm going to, because so many scale separations, I choose to use boxes that are size 1 by 1 by 4, and I've decreased the forcing scale of the turbulence to be about a fifth of, or to be a fifth of the vertical height, and that means that the eddies are 20th of the length of the box. So the mean field that you observe here is actually 20 times larger than the size of the eddies that are being forced. And this turns out to be basically converged because we doubled the box size and we saw that the wavelength didn't change. So this is an important point that you just need a lot of scale separation between your box scale and your forcing scale, and then also try to capture the effect of stratification and resistivity and everything. So basically, I'm going to use the diagnostics I'm going to use are going to be based on this picture of, so you're forcing the velocity scale, you have some hydrodynamic cascade that's going to be driving a small scale dynamo at higher wave numbers. And then if you observe growth of these low K numbers, then that's kind of characteristic sign of observing a large scale dynamo in your system. So again, the diagnostics I'm going to show is basically summing up all the energy in the lowest K modes of the box. This is going to be this E capital B as a function of time, and then looking at the energy in the small scale modes, in the small scale modes of the magnetic field, looking at those as a function of time. So to get on the same page, let's consider a very weakly stratified box. So basically stratification is important, and just compare a run with shear to one without shear. So the one with shear is shown in blue. The dashed lines are the energy in the small scale magnetic fields. You can see the small scale dynamo grows exponentially, and they both saturate within a few dynamical times. And in the case with shear, the energy in the mean fields, which I show in solid here, actually keeps growing until it reaches this quasi-saturation and has some wobbles, and eventually over some time reaches roughly equipartition with, maybe like 10–20% of equipartition with the small scale magnetic fluctuation. However, when you have no shear, the mean field just stays in some stochastic kind of equilibrium with the small scale dynamo spectrum. And I'll show the spectrum in a second. And visually, the way this looks is if you look at your toroidal field or your By field as a function of Z or a function of the polar angle, you see after the phase of the small scale dynamo saturation, you have a bunch of magnetic fluctuations in the box. As I mentioned, the magnetic shear current effect, that's when it can actually start growing, and then you see the evolution of a coherent mode. And physically, this is what your eye sees along the Z direction. And if you look at the spectra at different times, when you have no shear, that's this gray thing, that's just the small scale dynamo spectrum. If you keep making the box bigger, you will just see less and less energy in your low K modes. However, when you have shear at different times, from red to orange to blue, to green to blue, you see these low K modes just generating, taking in a lot more energy. And they actually have, individual modes have much more energy than the small scale modes, but the total energy in the low K mode is about 10% of everything that's in these high K wave numbers. Okay, and so now the interesting kind of experiment, I'm just showing a few parameters here. So we fixed the Reynolds number and increased stratification. So the way that looks is basically your small scale dynamo growth rate decreases as you go from blue to orange to green. It eventually shuts off when you're too stably stratified. And then you could see even at these intermediate stratification, at intermediate stratification, the large scale dynamo also actually continues to grow, although much slower. But if you run it long enough, it actually also reaches near equipartition. So, and you can see that in the isotropic, these are normalized isotropic spectra, that the two small scale dynamo unstable simulations, so the orange and the blue, maintain a large scale dynamo. So it seems broadly that the large scale dynamo appears to be unstable as long as the small scale dynamo is unstable to provide magnetic fluctuations. And this is for the magnetic shear current effect. Okay, and so in order to connect to this astrophysical kind of estimates, we, as far as we could, basically try to plot the saturation energy of the large scale dynamo and the small scale dynamo as a function of the buoyancy Reynolds number, the important dimensionless parameter here. So as you increase stratification, you can see that the energy in the small scale magnetic field steadily decreases. This is taken at the very end of the simulation once everything is steady state and saturated. And the energy in large scale magnetic field is ordered 20%, 10% of the small scale magnetic field, but it also dies when the small scale dynamo dies. And so this is basically roughly showing that the small scale dynamo seems to saturate near equipartition as long as the small scale dynamo is operating. And this is kind of my what I was talking about. The small scale dynamo really cares about the small scales, and in this one example, the large scale dynamo is driven by the small scale dynamo. So suddenly the large scales actually really care about what's happening at the mesoscales and the small scales. And so just as a order of magnitude estimate in the Tachocline. So if you imagine that, you ask the question, what level should a magnetic shear current effect possibly saturate at in turbulence driven by horizontal shear instabilities in the Tachocline? You use the RMS estimate for the horizontal shear turbulence in the Tachocline. It's about 100 meters per second. That gives you an equipartition value of about 1 Tesla. And maybe 10% of that, maybe slightly less, gives you upper bound of about 1,000 Gauss, perhaps, from a shear current effect, if you believe that this effect will go from the box to the sphere. So it seems relatively reasonable. Okay, so I have basically done. There's some conversion, but how much time do I have? Am I at 30 minutes? I forgot to start my timer.
More 5 minutes, perhaps.
Five more minutes?
Yeah, and
okay.
Yeah.
Okay, cool. So yeah, that kind of ends the kind of physics of the talk. But for those of you interested in shearing boxes, basically did a bunch of tests to see that everything that we chose was converged. Basically, the first question is, does aspect ratio really matter? Sometimes people do these shearing boxes that are highly anisotropic. I mean, is it just a result of it being anisotropic? Like, what if you actually did a full cube? And so we did that. We made boxes that are 2 by 2 by 4, and then full cubes, so 4 by 4 by 4. And this obviously takes a lot more resolution, so we can only do a few runs at each. And basically found that so keeping all other parameters constant, just making the boxes, the volume of your turbulence larger, you basically see a much more coherent effect the larger your boxes, and that's kind of due to a lot of this stochasticity being decreased in scaling as 1 over the square root of volume in your domains. And so you can see that the blue, orange, and green for the different box sizes, their spectra of saturation are basically very, very similar. And statistically, they're also very similar in terms of their evolutions. We try to do a bunch of ensembles and study that. There's this question of sometimes long-term evolution, that maybe this is a very transient phase. Basically, it seems that if you have a larger volume, so we're able to do the 2 by 2 by 4 box for a much longer time. So previously I was doing only up to like 500, but if you run it for like 3,000 correlation times, the bigger the box, the more coherent it seems to be. So this is a good sign of robustness. And then the last thing is, so there's from the dispersion relation, there's a prediction for the optimal growth, for the optimal wave number, wavelength of the mean field mode. And to make sure that you capture it, you should, if you double the z direction of your box, you shouldn't see the new mean field take the entire volume again. You should see it maintain the wavelength that it had. That's exactly what we see with if we do a 1 by 1 by 8 box, you could look at the spectrum at saturation. Basically, the dominant mode is this wavelength equals 4 box. So everything that I've shown you with the 1 by 1 by 4 boxes are basically the minimal convergence that you need to resolve a shear current effect in a box. So it's this factor of 20 of the scale separation, which is not often, I think, satisfied in the literature. But at least this is what you need for our parameters. And so the last question is this question of alpha quenching in alpha-based dynamos in boxes, at least, where you don't have helicity fluxes. So that's due to the presence of helicity in your turbulence. And because these shear current effects are driven by non-helical magnetic fields, they in principle should not be dependent on the magnetic Reynolds number. So you can keep arbitrarily increasing your magnetic Reynolds number, and it shouldn't change the saturation amplitude of the dynamo and also the growth rate of the dynamo. And so we tried to vary the magnetic Reynolds number by a factor of 4, and there's no signs of catastrophic quenching. And that's kind of what you expect. So as you increase the magnetic Reynolds number, your small scale dynamo growth rate increases. That's these dashed lines. But then the kind of evolution of the mean field all seems to roughly be very similar, minus just the kind of saturation behavior. And they saturate at very similar amplitudes. And you can also see that from the isotropic spectra. So that was kind of a detailed dive into magnetic shear current effects. But also you can study alpha effects in stably stratified turbulence. That's not something I've done. So to summarize, we numerically showed that the magnetic shear current effect is robust to stable stratification as long as the small scale dynamo in the hydrodynamic turbulence is unstable. This is kind of physically, you could think of this as you can grow near equipartition mean toroidal fields from scratch. So just having a shear flow and some small scale turbulence, you'll self-consistently emerge, the toroidal field can emerge. Large scale dynamos, they care about mesoscale and small scale turbulence, something to keep in mind. And at least in the shearing boxes, you need quite a large scale separation of at least 20 between your small scale turbulence and your large scale field. And so takeaways from the talk, just thought of 3. So large scale and small scale dynamos can spontaneously emerge in local regions of stably stratified turbulence and shear. Broadly speaking, strong stable stratification suppresses dynamo action, as you might have expected, and high thermal diffusion generally helps dynamo efficiency. And just want to say that asymptotic parameter regimes are crucial to understand when working in this field, because simulations can be deceptive. My prime numbers don't go below 10 to the -2, for example, but in reality it goes, they're 10 -4. So mesoscales and small scales and global simulations are usually quite diffusive, so you have to be very careful about interpretations. They don't properly capture stably stratified turbulence or alpha quenching. That's just the trade-off. But local simulations obviously don't capture anything realistic on large scales. So with that, thank you for tuning in. I'm glad to take any questions.
Yeah, thank you so much, Valentin. This was very nice. So we have a time for 1 or 2 questions before the last talk. Yeah, Bob Stein has the hand up. Please, Bob.
I have one comment and a question. The comment is that the very bottom of the convection zone is also stably stratified. So some of these considerations could apply there as well as in the Tachocline. My question is, since you're using the Boussinesq approximation, I don't understand how you actually can vary the stratification.
So the stratification is some background profile, right? And that background profile sets a local solid frequency, which is the only thing that goes into the Boussinesq approximation. So the equation I'm solving are the fluctuations on top of this background profile, which is kind of which is fully captured in the Bruner solid frequency, right? Because the Bruner solid frequency has radial derivatives in it of the density and pressure.
Yeah. Any more questions? Nick.
Made sense. Maybe there's a better way to say it, but.
Valentin, yeah, that was a very nice, thorough talk. Sorry, you only had a short amount of time to explain all that great stuff. I mean, some of the conclusions you reach are a little bit counter to some of the conclusions other people have reached more recently, like Cattaneo and Tobias, when they're trying to, I mean, they've been trying for years to find ways to manufacture large-scale flows, right? But mainly through regular alpha effects, helical alpha effects. So there they find that the thing you have, I mean, people have always been trying to amplify large-scale flows, and they eventually seem to conclude that what you have to do is suppress the small-scale dynamo flows in order for the large-scale ones to emerge. But you're sort of saying the opposite. Do you have any sort of comments or thoughts about why that is?
Yeah, so I think I think the key here is it's like a study of 2 different types of dynamos, right? So they're studying helical flows, and I try to emphasize that. So this is why this magnetic shear current effect. This was Jonathan Squire's original PhD thesis. It was originally actually in accretion disks, where people think there might not be a lot of helical turbulence in the middle of the disk. And so they're looking for a large-scale dynamo mechanism that doesn't have that's not driven by helicity in the small-scale field. So it seems to be that if you have non-helical magnetic fluctuations and a shear, then it works really well at magnetic Reynolds numbers. That's why this effect is so exciting. My understanding of the problem with helicity-based dynamos is that in order to grow the large-scale field, you need helicity in your small-scale magnetic fields. But then the growth rate becomes really slow because it takes so in order to grow a large-scale helical field, you need to dissipate the same amount of helicity at small scales, right? And so at very large magnetic Reynolds number, it becomes harder and harder to dissipate small helicity at the small scales. And so if you could do something kind of artificial, like really basically make your small scales diffusive, they'll dissipate helicity faster, and then you'll be able to grow large scale helical fields. The alternative is to transport that helicity out of the system, which is probably what stars really do. And so I think the question of helicity is what really separates kind of their studies from my kind of specific study of non-helical turbulence. Is that?
Do you think that shear current driven dynamos should be considered more upfront in the other circumstances, in convective dynamos?
Yeah, I mean, in convective dynamos, I guess you need some if you have some mean flow averaged. Well, so I guess in reality you have both operating, right? Because the turbulence, even when you have like helical turbulence, it's not 100% helical. If you measure helicity fractions, 10-20% sometimes. So in principle, both might be operating, both might be competing. And I think when you read these papers, people are like, I'm doing a really good job suppressing helicity because I just drive absolutely no helicity. When people do alpha squared dynamos or alpha omega dynamos, they just fully force helically, right? In reality, you have some instability that's creating some fractional helicity, and both effects might be operating, might be competing. That's something I think that isn't really explored. It's usually these idealists. So I'm on one side of the idealistic best case scenario for the shear current effect, right? And they're studying kind of like best case scenario for the alpha effect. And the reality might be some mix. And I don't know how they interact. I mean, that's a good question, or what's realistic. Yeah.
Thanks for.
Okay, so let's move to the following talk. But please, if you have more questions, please let your questions and thoughts in the Jamboard. And I hope Valentin stays a bit longer to discuss later with everybody about that.
All right, thank you.
I don't know if you have time later. I hope so. And now we go to Loren Matilsky. And Loren just finished the PhD too a few months ago, I think. And now he's working with Nick Brumel, Santa Cruz, I believe. And yeah, please, Loren will talk about Tachocline confinement by a Dynamo. That's exciting. So please take it away.
Sorry, I'm just figuring out my I've got this extra monitor. Just 1 second.
That's what you get for buying fancy new monitors.
I know, I just got it. Okay, I have my video, and then I need to share my screen again. Okay, 1 second. Again. Do you see my talk?
We can see your talk, but it's in the mode that
presenter mode.
Yeah, in your mode.
Sorry, I don't know what's going on. Hold on.
Yeah, you have to switch to which display you're sending to Zoom.
Yeah. Let me get Zoom out of the monitor. Okay. I think the problem was that Zoom was in the monitor and I just need my presentation in the monitor. Okay. Zoom, share screen. Okay. How about now?
Now it's great. Yeah.
Okay. Right. Okay. Sorry about that. I'm Loren Matilsky. I just got my PhD at CU Boulder, working with Yuri Tomre and Brad Heinemann. And today I'll be talking about one of our global simulations with the relay code that seems to reproduce a tachocline that's in a state of confinement via magnetic dynamo, which is exciting. And this is a paper that was just accepted for AppJ Letters. It's not quite out yet with journal numbers, but you can view the archive version of the accepted paper. And that's also, I think there's a link on the COFFIES website. Okay, so the solar tachocline, we spent all day talking about it. But to recap, the convection zone rotates differentially. The radiative interior rotates like a solid body. And I don't think we talked too much today about why that is actually surprising. The reason it's surprising is that helioseismology measures a width for the tachocline of about 5% of the solar radius, or I guess we learned earlier, closer to 1%. But if left to its own devices, Spiegel and Zahn in 1992, which we'll talk about in just a second, showed that via radiative spreading, basically the meridional circulation burrowing inward via the radiative conductivity would have imprinted the meridional circulation and the differential rotation downward on a hyperdiffusive time scale. And so this happens slowly. It happens on the Eddington Sweet time scale of 200 billion years, but because it's hyperdiffusive, this should have spread the tachocline downward by a significant amount. So by the age of the sun, it should have gone from where it sits roughly at the base of the convection zone today, basically all the way into the radiative interior. And so what this means is that there must be a torque that's forcing the radiative interior to rotate like a solid body. And the origin of this torque has launched a few different tachocline confinement scenarios, as they've been called in the literature. So there's two primary scenarios, and they take different names. The first was proposed by Spiegel and Zahn in 1992, which is the fast or hydrodynamic scenario. And basically this says that shear instabilities would, in a strongly stratified medium, tend to transport things horizontally rather than vertically. And so this could create a Reynolds stress that would smooth the angular velocity on spherical surfaces and effectively enforce solid body rotation in a boundary layer just below the convection zone. Goff and McIntyre in 1998 said that no, this was not likely. In fact, in the Earth's atmosphere, these same instabilities should drive the system away from uniform rotation, not toward it. And they postulated in kind of a famous paper, which is depicted in the middle, that there must be a magnetic field in the radiative interior. And so this followed from a long line of thought that magnetic fields in radiative interiors could affect the differential rotation. I mean, this goes back to Ferraro, 1937, which we'll also talk about. But their new finding, the big claim of this Nature paper, was that there had to be a dipolar or some type of primordial field in the radiative interior. I should mention, though, that there's also different flavors for the magnetic field. So if there's not a primordial field and you buy that there has to be a magnetic forcing going on to keep the tachocline there, then you could also get a magnetic field from the cyclic dynamo above. And so this is a fast MHD scenario. I should mention that the Goff and McIntyre model well, the reason it's fast is the shear instabilities work, as Peter Gilman talked about, on the timescales of days to years, which is fast compared to the Eddington Sweet time, whereas the slow Goffin-McIntyre MHD scenario works on the timescale of Eddington Sweet, so billions of years. But and then the cyclic magnetic field, if that could diffuse inward, that was basically imposed from above, and then diffusing downward to a skin depth, that would operate on the timescale of 22 years or decades. So that's a fast version of the MHD scenario. And also, just as a preview, this fast scenario is basically what my simulation is falling into. Okay, and then I should talk a bit about tachoclines in global simulations, because in global models, things are a bit different. In the solar case, things are very strongly stratified, which means that Froude number, or the ratio of the buoyancy frequency to rotation rate, is quite large, and also the Prandtl number is very small. When that happens, radiative spread is the thing that dominates. In global models, typically, I'm not aware of any global model that can actually get into the radiative spreading regime. And so instead, global models tend to have an eddy viscosity or some equivalent that is quite high. And so the tachocline spreads via viscosity instead of radiative spread. So already I should preview that the global models are not well positioned to tackle the full confinement problem. But they are positioned to tackle the viscous spread, which we don't really know, but it might not be too different than radiative spread. Anyway, simulations with tachoclines typically enforce the tachocline in some way. In ASH, this is done via an explicit drop in the viscosity. Basically, you have to lower the viscosity enough that the tachocline doesn't have time to spread inward. In ASH, it's done explicitly in some of Gustavo's papers, and also the rest of the OILAG community. It's more self-consistent. It's an implicit drop in the diffusivity because there's weak motions in the radiative interior. That's in the ILES simulations with OILAG. Anyway, here are two examples. One's from Sascha Brun, 2011, and then Gustavo from 2016. And the pro of this approach is that you basically are guaranteed to get a tachocline. And then you can study the tachocline's effects on, say, the dynamo. I think one con is that the tachocline is likely temporary. We don't know how long it takes to diffuse away, but it's not in a steady state, because no matter what you do, the diffusion is still there, and it's going to slowly imprint the differential rotation inward. The approach that we use is basically not to lower the diffusions. So allow the differential rotation to spread inward, and then in the MHD case, see what happens if you add a magnetic field. And at the outset, well, we don't know if that's justified. The diffusivities are meant to represent subgrid scale motions. I mean, we do them for computational tractability, but there should be some motion. But I want to mention, though, a spoiler alert, that there is actually motion in the radiative interior. There's strong horizontal motions. And so a priori, having the eddy diffusivities large in the radiative interior might not be so bad, but we can also argue about that after the talk. Okay, so I've been using the Rayleigh code, which is an anelastic spherical harmonic solver. It's descendant of the ASH code, but originally was developed by Nicholas Featherstone at CU Boulder. It's now open source, and basically it solves the anelastic or Boussinesq equations in spherical shells. It's a pseudospectral code. It expands variables in Chebyshevs in the radial direction, spherical harmonics in the horizontal direction, and computes linear terms in spectral space and nonlinear terms in physical space. but it's quite efficient. It's highly parallelized, so it scales up to, I think, a few 100,000 cores. And it's a very efficient tool to study convection and dynamos and spheres. So this is a sample of what the flows actually look like. It's large scale and global, so we're not capturing the small scale turbulent cascade or anything like that. But we hope we get a reasonable depiction of what the large scale flows might look like. My case is anelastic. So there's strong density stratification across the layer, but sound waves are basically filtered out because we demand that the divergence of the mass flux be 0. Here's my computational domain, and I will only discuss 2 simulations in this talk. One is hydro or HD, and the other is MHD. So these are the non-dimensional input parameters. We're running basically a reasonably turbulent system. We're maximum turbulence that we can do with the resolution available. Probably 10 to 100 times supercritical. It's actually difficult to figure out what the critical Rayleigh number is for these models. So unfortunately, I don't know the exact number, but I would say tens to hundreds of times supercritical in terms of the convection. And then we have 2 cases that are identical, except for one has a magnetic field. And these are some of the output parameters. So our Reynolds number is moderate in terms of, on scales of 10 to 100. And in the sun, it's like, I don't know, 10 to the 10. So not as turbulent as the sun, but we hope we're capturing large scales. And just a bit, I want to mention my background state because it's a little different. It captures basically a portion of the radiative interior and convection zone. It's stratified, so gravity scales as 1/r². The reason it's a little different is there's a fixed internal heating profile. Well, okay, there's 2 reasons. One is that the background density is just slightly super-adiabatic in the convection zone, and then a constant strongly sub-adiabatic in the radiative interior. So it's not taken from a solar model. It's just meant to capture the change in stable stratification that occurs at the interface. And then it's internally heated. So the way the convection gets set up is that we have a Q that mimics the radiative heating. It's similar to standard solar models like Model S, but it basically heats things from below and sets up a temperature difference across the convection zone. So the background stratification is actually neutrally stable in the convection zone, and then this internal heating sets up the temperature difference that makes it slightly super adiabatic. And the main other thing is that the diffusivities, which are basically our crude SGS treatments of the subgrid scale processes, do not plunge as you go into the radiative interior. So there's still substantial diffusion at all parts of the shell. And we get a dynamo in our MHD case with convective overshoot. And so here's a picture of what the flows look like. On the left, we see the velocity components as a function of radius. These are RMS convective velocities, so the longitudinal mean has been subtracted out. And the blue line, you can see the vertical velocity plunge by about 5 or 6 orders of magnitude over the overshoot layer. So in these plots, the black line is the base of the convection zone. The green line is the base of the overshoot layer. So it's a fairly thin overshoot layer. And then deeper down, we'll see that's the location of the tachocline, or the base of the tachocline. We can also look at the magnetic fields, and these are strongest in the overshoot layer. And they also decay in the radiative interior. they become largely horizontal. I should mention for the velocities, these motions are basically purely horizontal in the radiative interior. And importantly, the horizontal flows are still significant. So there's very little vertical motion in the radiative interior, but I'd say one of the key points is that in this simulation and in other simulations that I'm aware of, the horizontal motions are actually quite strong. In this specific case, it's the same is true for the magnetic field, but a little less. There's still some substantial magnetic field, radial magnetic field in the radiative interior, but it gets to be mostly horizontal fields. Okay, so the key result of all this is that the MHD case has a self-consistently confined tachocline. So in the hydrodynamic case, the differential rotation viscously imprints all the way into the interior. That's the picture on the left. And then in the MHD case, the radiative interior is forced into solid body rotation. And this lasts for a very long time. It's statistically steady for about 10 magnetic diffusion times across the magnetic interior. So there's no evidence for any kind of secular drift. And as we'll see in a second, it's actually in dynamical balance. And so it seems like it really is held there in solid body rotation. And we know it has to be due to the magnetic field because the HD case had no magnetic field and the MHD case does. But we'll talk explicitly about how that happens in just a second. I should mention this is a tachocline. It is not the solar tachocline. There's a lot of differences between my model and the solar case. Mainly, the rest of the differential rotation in the convection zone is quite weaker than in the solar case. And also it's not really constant along radial lines. And so it's a different kind of tachocline. So I've defined somewhat arbitrarily the thickness of the tachocline to be where the rotation rate becomes like a solid body, and measure that from the base of the convection zone to that location. Okay, so to understand how this is happening, why the magnetic field is forcing solid body rotation, we should look at what the field actually looks like. And so I've been calling these things partial Reits. So first, these are projections of the full sphere in Malwadi projection, and I'm showing the toroidal component. So if we focus on the panels up top, I'm showing the toroidal component at left, the theta component in the middle, and then their product on the right. And I've been calling these things partial Reits because they seem to wrap partway around the sphere. For m equals 1, there's 2 partial Reits. So you can see actually 2 different types of modes in this model. Mostly it's m equals 1 in the north, and then m equals 2 in the south. But basically the field is concentrated on m equals 1 or 2. And the field links both zones. So each, you can see that in the convection zone, or this is actually the base of the convection zone, the field is fairly turbulent. It's getting pummeled by the convective flows, but it bears the same signature as the field in the radiative interior. In both of these zones, there is poleward angular momentum transport. So that's, I mean, that's the giveaway for how this is working to confine the tachocline. We'll get more into this in a second. But basically, when you multiply these 2 components together, you get something that's on average positive in the north and negative in the south. And if you work out the Maxwell stresses, that means there's a poleward angular momentum transport. And that's giving you a magnetic torque that's forcing solid body rotation. This is a complicated system. So the fields are non-axisymmetric, everything is non-linearly coupled, and it's also a cycling dynamo. So the way this works is it's a little bit strange to think of polarity reversals when it's non-axisymmetric. Normally we're thinking of the polarity of the m=0 component. And so instead, I want us to think about the polarity of the m=1 component. And the way that I do this is I take the phase of the m=1 field, say for b theta. So this is the real part of the m=1 transformed b theta, and then plot that as a function of time and radius. And the reason I do that is because the different parts of the system seem to correspond to different phase differences. In particular, so you can see the polarity reversal in the m=1 component taking place about every 500 rotation periods, but it's irregular. And also the dynamo seems to be led by the overshoot layer. So the polarity reversal first appears in the overshoot layer and then propagates downward. It's a little less clear. It might also be that the convection zone is reversing polarity first, and then that propagates down into the overshoot layer, but it's a little bit unclear at this point. But the main thing that I think is important is that the imprinting rate of the field into the radiative interior is roughly commensurate with the skin depth speed. So in the argument for the fast confinement scenario, MHD confinement scenario, you're forcing something, a field with a cycle of 22 years, and that propagated down to a skin depth. In my case, of course, the skin depth is a lot larger because the diffusivity is quite larger, but it's still the same type of thing. And so if you take the 500 rotations and think about how quickly the magnetic field should be diffusing inward, it's basically consistent. That's these slanted lines here. So overall, this confinement, if, as I'll show in a second, the magnetic field is really what's confining things, it's consistent with a more complicated fast MHD scenario. So here is an explicit verification that it's actually the magnetic torque that is fighting viscosity to achieve solid body rotation. So the way this is happening is that there is sizable latitudinal differential rotation in the convection zone. Viscosity seeks to imprint that downward. In my case, the differential rotation is confined mostly to low latitudes. So it's a, instead of a fast equator slow pole, it's more like a fast equator slow mid-latitude regions. But anyway, the viscosity seeks to speed up the equator and slow down the mid-latitude regions. If you look at the torques in the tachocline, here are all the torques. The viscosity is in orange. And you can see that the magnetic torque basically opposes it everywhere. The other torques that could play a role, like meridional circulation and Reynolds stresses, are negligible in the tachocline. This is the full torque equation. I'll focus on the magnetic term in a second. But what I'd like to point out is that the magnetic torque is actually due basically entirely from just the m=1 and 2 contributions. So it really is the non-axisymmetric magnetic field that's doing the confining. The way we can verify that is, well, physically, the way it's working is that we have non-axisymmetric fields, and they're relatively in phase. So you can multiply the two of them together and you get two non-axisymmetric fields. They're in phase and longitude, and you multiply, say, b theta and b phi together, and you get a product that's axisymmetric. So the product of non-axisymmetric fields can make a an axisymmetric torque. That's what we were seeing when we were looking at the product on the Malwadi projections. And furthermore, you can do the same thing in time. You can have a cycling magnetic field whose product is time steady. And so what's happening is that you have a non-axisymmetric cycling magnetic field that's producing a axisymmetric time steady torque. Mathematically, what I did was basically just Fourier transform each component of the field and then multiply like m's and frequencies. And so when I said that the torque was due purely to the m equals 1 and 2, I meant that when you just looked at the contributions of the torque from the m equals 1 and 2 components, that reproduced basically everything. So that's this dotted blue line, and you can see that it basically gives you all of the magnetic torque back. And what's really interesting is that if you look at the frequency components of the fields that are producing the torque, all of them work together to confine the tachocline. So we can sort of understand that this from the idea that we can understand why it's just m equals 1 and 2, because that's where most of the field lives. And also if they're roughly in phase, then they should be able to produce a zonally average magnetic torque. In frequency space, if they're all, so this is, say, if you look at the m equals 1 component as a function of frequency, each frequency basically gives a magnetic torque that is positive at higher latitudes, negative at low latitudes. It's fighting the viscosity. And it's roughly the same across the relevant frequencies of the magnetic field. And so this means that the fields are also really in phase in time, and that each frequency component of this complicated dynamo is working separately to confine the tachocline. And if you think about it, what this means is that this is a local process. So if you have differential rotation that shears a colloidal magnetic field, it will locally try to eliminate that shear. So the way this works is essentially like Ferraro's law, which goes back to 1937, that isorotation contours in radiative interiors would tend to fall along colloidal magnetic field lines. But the way it all works is actually fairly simple. If you impose a differential rotation on an initially, say, dipolar colloidal field, it will stretch that colloidal field and produce a magnetic tension force that will pull back on the colloidal field lines and attempt to eliminate the shear. And in the axisymmetric time steady version of this, we get Ferraro's law, which is the rotation contours falling along the colloidal field. In the non-axisymmetric cycling case, it's actually quite a bit more restrictive. This was realized by Missel and Weiss in 1987, and this would actually tend to yield solid body rotation. And it would be basically a local process. If you impose a shear of a length scale, of a certain length scale, then this kind of non-axisymmetric Ferraro's law would eliminate the shear on an Alfvén crossing time of that shear. And it's hard to verify if that is explicitly what's happening in our simulation, but it seems to be consistent with it. If you look at our cycling timescale, that's around 500 rotations, whereas this Alfvén crossing timescale of the shear is about 40 rotations. And so this is consistent with kind of a slowly varying magnetic cycle that at every instant is getting, is forcing solid body rotation on a much quicker timescale. Sorry, how much time do I have? I think I'm
more 3 minutes.
Okay. I'll let me, okay, I'm almost done. I'll speed through this. So the main thing that we need to know is why is the radiator interior magnetized? What's producing the magnetic field? For the toroidal field, it is effectively mean shear. So here I've been looking at a magnetic energy equation. So basically I take the induction equation and multiply by b phi. I'm sorry, it's not shown on the slide, but this should be b phi squared, and then all these terms should be multiplied by b phi. Then I take an average, and effectively I'm figuring out the production rates due to different processes of the toroidal field. The toroidal field is quite simple because most of the production is all via mean shear. And that makes sense. If a process like Ferraro's law is working, then the toroidal field should basically mostly be coming from the colloidal field. There's also magnetic pumping in the overshoot layer that's sending toroidal field from the convection zone inward. But the really interesting thing is that if you look at the theta component, that also seems to get produced inductively. So again, this is an energy equation. So imagine this equation was multiplied by B theta. Interestingly, the inductive production is positive. And so this means that there is local dynamo amplification in the radiative interior. You can look at which terms are actually producing the magnetic field, and it's mostly compression and shear. In the tachocline, deeper down, it's almost exclusively compression. And I just want to point out that this is not a complete dynamo loop. I mean, we're basically, the diffusion is also sending colloidal field downward, but there is dynamo amplification. And so this is an interesting possibility that on the large scales, if you have an initial B theta, then it could get locally amplified. And then finally, this is more speculative, and I think Peter Gilman probably knows more about how this could work. But deep down, we find that our motions are almost entirely Rossby waves. And so deep in the shell, it seems like that should be what is producing the colloidal field. This is just mentioned at the end of the paper. You can actually see classical equatorially confined Rossby waves in the simulation quite well. They follow the right dispersion relation. And then I'll just end with the idea that the horizontal motions, they seem to be ubiquitous in global simulations. So they're in the two simulations I presented today. They seem to be present in OILAG as well, and in ASH. And I think there needs to be more of a investigation into what these horizontal motions are actually doing. If they could be leading to dynamo amplification or something like that. And that's basically it. Just to summarize, we had a fast MHD confinement scenario in a 3D model. And this was confinement from a non-axisymmetric and cycling magnetic field. The scenario was consistent with a modified non-axisymmetric Ferraro's law. And the magnetic field entered the radiative interior via diffusion and also was amplified by horizontal motions. And the horizontal motions might be Rossby waves. I mean, they are deeper down in the tachocline, it's not as clear. Thanks for your time. I'm happy to answer any questions you might have.
Thank you so much, Loren. This was a very nice talk. And we have already some hands up. I don't know who was first. Sushan, maybe you were first.
Yeah, thanks, Loren. It was really nice to see the discussion, especially on what magnetic tension would do when the omega effect is operating. Can you go back to that slide when you had the cartoon of
Whoops.
Tension opposing
rotation?
Yeah. So here, the shear in latitudinal differential rotation is creating the magnetic field, would magnetic tension actually slow down the rotation rate everywhere, or would it accelerate the high latitudes and decelerate the low latitudes?
Would it accelerate the high? Well, I think that is what it's doing. In my case, it's accelerating the higher latitudes.
Right. So the green arrow at the high latitudes would be to the right, and at low latitudes to the left.
Oh, yeah. Sorry, this is sort of if you look at the cartoon, I guess this would be in a non-rotating frame, so everything is.
Oh, okay. Yeah, the magnitudes are different. So
Do you love to going dancing or not?
I don't, unfortunately.
Okay.
Actually, I should think about that, because then the shear perturbation
Yeah, because I had the
negative.
same theoretical expectation, which is published in my thesis in 2019. And yeah,
I might have reversed. You might be right. I might have reversed. These top arrows might I'm not sure. I have to think about that. I might have gotten some of the arrows reversed.
no worries. Yeah, we can talk about that later.
But the key point is that locally, this process would tend to oppose whatever shear is getting imprinted. I think that's the main point.
Yeah, thank you.
Yeah.
Bill?
Yeah, I just had a very nice talk. Thank you. I just had a quick question regarding the initial magnetic state for your domain.
Right.
How did you start it? Was it a seed field throughout the entire domain, based, imposed upon your hydrodynamic state, or how did you?
Yes. No. So it wasn't imposed on the hydro case. That's actually an interesting next problem: is can this process actually eliminate differential rotation if it already has made it into the radiative interior? But I initialized them separately, and I put the magnetic field only in the convection zone. So it's some form of Gaussian noise distributed across spherical harmonics. I think in reality, it doesn't matter. I put it in just the convection zone to see if it could make its way into the radiative interior. I think the diffusion is high enough that the initial fluctuations would migrate inward anyway. So I don't think there's too much of a difference between just putting the random seed field anywhere. But yeah, it's a random seed field, amplitude of about 1 Gauss, and then it grows to amplitudes of about a few kilogauss.
Okay, great, thanks.
Yeah.
Valentin?
Thank you, Loren. It was a great talk. Just a question on scale separation. I don't actually know the numbers, but in order for you to get your fields into the Tachocline and have an induction loop, you really need to, I guess, penetrate through that layer. And I was wondering,
Yeah.
So as you're saying, your simulation, it's very viscous. You have what can you do? But in reality, there's some estimates for the convective penetration depth. And I was wondering what that scale is relative to the Tachocline thickness, because if it's much smaller, I would imagine this pumping mechanism to get it into that strong shear layer might be inefficient kind of in the actual system. Because I think in your case, the penetrative length seems to be comparable to the Tachocline. So I was wondering if that's realistic or not.
I would say if you're just thinking about a skin depth argument, it's might not be realistic. So the original fast confinement scenario for Skoutnev, sorry, I don't know how to pronounce the name, but they did all this, and they need a turbulently enhanced magnetic diffusivity to make the skin depth large enough for the field to get past the Tachocline. I think what's interesting in our case is that all the different even the low frequency components seem to be working to confine the Tachocline. And so I don't think the skin depth is necessarily the right parameter in this case. And so if you had some magnetic field that was diffusing inward, say on the molecular diffusion timescale, it's hard to know how it all play out, because on the one hand, my magnetic diffusions are far too high, but also the viscosity is far too high. So it might be that a very slowly diffusing magnetic field could confine the Tachocline, since the Tachocline is also very slowly diffusing inward. But I think you're right that if the diffusion is the primary effect getting colloidal field into the interior in the first case, then there's real questions about what is the consequence of choosing a magnetic diffusion that's quite high. If I want to chat with you more about your small scale stuff. If there's an instability that's already producing colloidal field in the interior, then maybe dynamo amplification could happen. If it really is Rossby waves doing it. That's more speculation though.
Yeah, so I guess you probably did this, but your initial profile, you had some stable stratification and then went to neutral, right?
Yeah.
So you chose that jump to be some strength. And
yeah.
I'm sure you played with that. Like, just sorry to take up time, but
No worries.
Yeah, like was there some behavior as you increased that the difference between the stratification and the neutral?
Yeah, I mean, it affects. I didn't play with it too much. I mean, I wanted to get as close to the solar strat, so it's quite stiff. I'm doing something that's on the order of the solar stiffness.
Okay,
but
so if you
mainly
did more stiffness, it wouldn't do much, you're saying? Okay.
If you lower the stiffness, what happens is the flows overshoot farther. So the depth of the overshoot layer gets bigger, and also the flows are stronger in the radiative interior. It's actually interesting. So if you did decrease the stratification enough, then you'd actually you'd get into the correct parameter regime as far as the sun is concerned. Maybe, I'm not sure if we could do it, where instead of viscous spread, you get radiative spread, because the really strong stratification is a lot of the reason that we can't get into that regime.
All right, thank you.
Yeah.
Nick, a very short question, maybe?
Yeah, I think a lot of the stuff that I was going to say has already been sort of brought up a little bit. I mean, Loren and I have talked about this a little bit already. I think an interesting experiment to do would be to, take the end of your hydrodynamic simulation, which has differential rotation already spread, and then start the dynamo calculation and see if the stresses, the magnetic stresses that you're doing actually eliminate or homogenize, not only cause a tachocline, but homogenize the interior. Because I think there's this question of, what homogenizes the interior. And right now you have these, Rossby modes or MHD Rossby modes of some sort, inductive modes happening there. And your process of getting them there is diffusion. And, how do you argue that? Because you have to take what happens in the limit of low diffusions in all of these things. Your magnetic stresses right now are viscously balanced. Your process for getting that homogenization is magnetic diffusion as well. So what happens in the limit of sort of high Reynolds numbers for these things, I think is the big question. And I think it would be nice just to do this. It's kind of like doing a weak scaling and strong scaling argument for, this technique, whether it works or not.
Right.
Start it with the differential rotation and see if you can eliminate
it. Yeah, no, I think that would be a good next step.
Okay, thank you. Oh, you have more.
No,
go ahead.
It's okay.
I see Brad has a question, which I'm curious about because.
Oh yeah, Brad. Brad.
It's actually a follow-up comment to what Nick was just talking about. I agree that running the simulation he suggested would be really interesting to actually see how the shear gets eliminated. It might also be an interesting case that we don't really care about the convection zone for this particular question. File it off and hammer the top with something like what the convection zone is doing, and see how the radiative interior responds. And the reason I'm suggesting that is because much of your time stepping and all of the numerical nastiness is being set by the convection zone and not the radiative interior. And you might be able to run something that for a lot longer that has a lot lower diffusion.
Yeah, that's true. I mean, effectively, that's what Nick, effectively you did that in a local scenario. But yeah, I think it would be interesting to extend to like an anelastic global model and see if you could capture meridional circulation, for example, global scale stuff. Yeah.
Okay, so I think it's time for discussion now. So there are a good number of comments in all the pages of the Jamboard. So the idea now is that we will split this good number of people that we have, a good number of participants. We are 26 now, and don't go. I see the number is decreasing. So the idea is that we separate into maybe two groups, right, Nick? we were thinking 3 groups, but now we are 25. Maybe 2 groups is fine.
Yeah, 2 groups is fine. Although maybe that screws Shay up because you probably already set us up for 3.
I did, but it shouldn't take too long to adjust. And that lets Brad off the hook.
Which is
Okay,
always
so-
a good thing.
So we will separate and we will discuss the notes, questions, and comments that are in the Jamboard, and always having in mind the 2 questions that Nick presented this morning. After this discussion, we will get together again, all of us, and we'll give us some important points that came from these brainstorm sessions separated. So I think Nick will be the facilitator in one of the groups, and I will be the facilitator in the other one. We asked Brad to help us, but I think it was in the case that we have a lot of people, and many people just already left. So thank you, Brad, for beginning collaborating with us. So Shia.
I just want to hang on, but before we go, I just want to add a quick point. This is low pressure. This is your chance to say anything you've been thinking about, and the Jamboards are up there to stimulate your thoughts or to remind you of something you thought of later, or something you thought of earlier, or something that somebody else thought of earlier. But this is feel free to bring up anything at this point, and let's just sort of see what random ideas float to the surface. So go for it. Be as creative as you want.
Are we ready?
Yeah, I think we're good to go, Shay.
All right, here you go. Oh, wait. Okay.
10 people in the other room.
Yeah, this is our gang. The other people are still going, I guess.
Yeah, and I'm gonna have to quit soon.
Yeah, that's okay. People are tired, and I was trying to keep these discussion sessions fairly short because I know it's the end of the day. Shay, where's the rest of it? Oh, we don't have Shay. Where's the rest?
It's gave them the 1 minute warning. They'll be here in 15 seconds at the very late. Like,
oh yeah, that's okay. Yeah, I forgot about the 1 minute warning. We all ignored the 1 minute warning. Oops.
Here they come.
Yay! Here's everybody. Okay, getting people to speak sort of decimated our audience down to 18, unsurprisingly.
Nishan was speaking just.
Yeah, he was speaking and got cut off, right?
Yeah, so if
Yeah.
you want to go and finish, Nishan, just very quickly.
Yeah, go for it.
Absolutely.
No worries. So one of the plots that
Nishan, Sushant.
Thanks, Gustav.
Sorry.
In one of the plots that Loren showed when he was comparing Goff and McIntyre and the other scenario in which magnetic fields were leaking through the radiative interior inside the sun. And so when a field reversal happens, or the dynamo operating in the convective zone was also kind of creating and inverting this field all throughout the sun in the radiative interior. If that actually happens, then that means the magnetic energy budget of the solar dynamo would be at least twice as high as we expect from dynamo just operating in the convective zone, right? Because it's also creating field for the radiative interior. So I thought that was just something new that I thought about from the talks today.
Yeah, no, I actually hadn't thought about that. That's interesting. Yeah, I mean, just spatially, you've got a much larger reservoir of energy to draw magnetic field from.
Yeah, good point.
If it could rise to the surface, then that might have input. But I don't know. I don't know if we'd know about it even if it were.
Yeah, if we somehow narrow down which reservoir magnetic energy comes from, then we'd see twice the effect than we see from our estimates of magnetic energy just from sunspots coming through, because we won't be factoring in the reversal of the field throughout the interior. And I guess that all that reversal that happens below the Tachocline would all just be kind of resistive heating, I guess.
Yeah, I don't know. I mean, I've been looking at it as kind of the convection zone is doing everything, sending field inward. Maybe the radiative interior helps amplify that field, but the convection zone is still sort of where most of the energy comes from.
Yeah, I have some simulations with Tachocline, and I believe that there is an alpha effect actually in the radiative zone. So I've been working on that, trying to look for instabilities that can provide an alpha effect. And Guilherme was here, but he's not anymore. He's looking for this using the test field method. But I tend to believe that there are instabilities driving this alpha effect. At least I can see that there is M=1 magnetic field instabilities, and I can also see magnetic buoyancy instabilities. So perhaps there is an alpha effect operating there in the radiative zone too.
Yeah, I was going to say these are likely buoyancy instabilities, right?
There are buoyancy instabilities too, and there are also kind of tipping instabilities, like Peter mentioned, or more like clamshell instabilities. Look more like clamshell instabilities. Yeah, so we are losing people. Nick, you're mute.
I'm not surprised, and I don't want to force people to.
Yeah.
I mean, we can let people's minds what's the word, cogitate on this for a while, and we can revisit it in another meeting coming up. But just to summarize what I mean, I think our random distribution of people put all the helioseismologists in mine and all the models in the other one, which is something we thought about doing and then decided against. But oh wait, that's just somebody with a higher power had a better plan for me.
Yeah, I definitely randomly assigned, but I was noticing that also.
I believe you, thousands would. But no, the thing that came out of our chat, and if I can summarize, was, you know, what are the possibilities moving forward for helioseismology? So this idea of, you know, trying to detect Rossby wave type motions. I mean, Rossby waves are becoming more and more and more. I mean, we used to think that they were just, yeah, sort of a byproduct. We didn't really, things look like Rossby waves, so what? But now it's becoming clear that they could be dynamically more and more important. So the vague possibility of, you know, detecting Rossby waves sort of deep down by Moe cupping techniques, as people were chatting about, would be exciting. And then we also discussed a little bit about Srijan Das's talk the other day about the possibility of, you know, those wonderful slides of all the magnetic kernels, but the possibilities of detecting some magnetic things. So those seem like possible movements forward. I don't know whether people from the other room have comments on this or thoughts on all that sort of stuff, detection of Rossby waves or detection of magnetic fields.
We thought that we are blind regarding helioseismology.
Brad was skeptical, but
I was violently skeptical, actually.
About which? About Rossby waves or about magnetic fields, or both?
Magnetic fields I'm very skeptical about, because we've been thinking about it for 30 years. And there's all sorts of reasons why even if you made a detection, you wouldn't really know whether you were detecting a magnetic field or something else. Rossby waves, people haven't thought about it enough. As you say, it's just entered into people's brains again, because of the observations of actual detection of Rossby waves. But they're not the same beasts. I want to point out there's an old paper by Wolf and Blizzard that shows that there are two families of Rossby waves. There are Rossby waves that live in stable regions, and there are Rossby waves that live in unstable regions, and they have distinct frequencies and they don't communicate with each other. And so the stuff that is being seen at the surface by the Max Planck group are probably not the same Rossby waves that would be living in the radiative interior and doing all this magic for us.
Oh yeah, great. I mean, thermal Rossby waves are just, you know, the cartridge belt that we, you know about. Booster columns, you know, it has a million different names, right?
Sure, and those still haven't been observed yet.
Yeah, I guess that's part of the
problem.
And
I'm publishing papers on them right now, so I feel the heat. But
well, that's the convective conundrum. That's somebody else's problem, right? Where's Nick Feathers?
Sure.
But so, Peter, what do you think? The Rossby waves can be sufficient to modify substantially the differential rotation?
Well, modify it somewhat. The nonlinear simulations I've seen, you know, it does oscillate, but not as a large fraction of the kinetic energy in the differential rotation. It's a smaller thing than that. Mm-hmm. That doesn't mean it's dynamically insignificant. It's still quite significant. You add a magnetic field and you may get more out of that. But, you know, we should keep in mind that at least at the surface, the differential rotation of the sun, leaving aside torsional oscillations for the moment, the differential rotation of the sun is amazingly steady. I mean, if you compare it to the Earth's atmosphere, the jet streams, the mean flows, they're a lot more meandering than the sun's differential rotation is. I've always been kind of fascinated by that it holds it so steady. The only systematic motion we've ever seen on global scales that is not the average differential rotation is the torsional oscillations, but that's a 0.5% effect.
Yeah,
really small. Now that doesn't necessarily have to be the case at all depths, but and we would estimate from the kind of things we've done in the nonlinear regime, you know, maybe a 10% effect in the base of the convection zone, but how much of that you could see at the surface is another question.
Mm-hmm.
Peter, do you think so? The problem in the sun's tachocline is probably not one of angular momentum transport. It's probably one of thermal transport. why isn't the Tachocline spread thermally over its lifetime?
Well,
Have you given any thoughts to thermal transport by Rossby waves and other motions in the Tachocline?
you mean a baroclinic wave where it's,
I don't even know what I'm talking about. So
well,
I'm just any sort of turbulent motion, either wave or otherwise, thermal transport.
well, all
Sort of a
I mean, look, to my mind, maybe this is oversimplified, but the only thing you have to have in order to keep the tachocline from spreading ever further down is an angular momentum cycle where the convection zone is putting angular momentum in at low latitudes. There's a horizontal process of some sort that transports it from low to high, and then it's putting it back into the convection zone at high latitudes. And that can be Reynolds stresses, that can be Maxwell stresses, some combination. And I
you don't think that the Tachocline's in thermal wind balance?
Well, even if it is, it's not, well, what I concluded from all the instability studies, doesn't take much of a magnetic field to stabilize that thermal wind. Whereas even a modest toroidal field can destabilize the latitudinal differential rotation. So in terms of the source of instability, I would say it strongly favors the latitudinal differential rotation as the energy source for that instability, and therefore it's a quasi-horizontal kind of thing. Now you may get in the full problem some heat transport going with it, but I don't. I mean, I've always been a fast tachocline guy. Let's put it that way. I've never quite believed in the really slow tachocline stuff. It's a nice theory, but I don't see that's relevant to solar cycles or anything else on short time scales.
Mm-hmm.
Maybe that's controversial, but that's how I think about it.
No, it's difficult, right? I mean, it's a matter of what, I mean, superficially, all the, fast things are, I mean, much more obvious, right? Much more present, but does the sort of very, very slow and steady process win the long-term race?
Well, but but in order to expand that tachocline further and further down, it means you're sending momentum further and further down. But if you have a closed cycle where it never gets very far, it just goes from latitude to high latitudes, I mean, and angular momentum cycles are ubiquitous in nature. I mean, the Earth's atmosphere and the ocean of solid Earth has one. And the transmission of the stress at low latitudes is put on it by the mean winds, is transmitted through the Earth by elastic stresses, and it's extremely fast. And I don't think that does anything. I don't think there's any influence of what's happening on the surface in the liquid core, zero. It's the same argument, basically.
I mean, in some sense, the magnetic field is also sending angular momentum to the pole. I mean, you're just plucking a magnetic field line and it travels along the field line to the pole.
In the instabilities I was doing, it's actually what's breaking down the differential rotation is the Maxwell stress, not the Reynolds stress. That's what makes these smaller differential rotations unstable. If you don't have that, the magnetic stresses, then the tachocline will support a somewhat larger differential rotation without being unstable.
Sorry, I need to get running. It's already 6 p.m. on the East Coast here, and I have
Yep.
to be somewhere. But anyway, thank you for the invitation and great discussion. And I'm on the coffee stuff, so I can always hang out sometimes.
Yeah, we'd love to have you participating, Valentin. So thanks very much for joining us today and speaking. It was great.
All right, thank you. Take care, everyone.
Thank you. Bye-bye.
Nick, are you going to say anything about distributing the slides for everybody's talks, or what? Maybe you don't have them all.
I will. I mean, I think the general idea is we'll try and get slides from all the presenters, and they'll be available on the COFFIES website, and also
Okay.
the
Great.
recording of this whole meeting will be available on the COFFIES website.
Mm-hmm.
Okay.
So that's the plan, unless somebody has a strong objection to putting their slides out there.
Okay.
Thank you for your permission already, Peter. Well, I think everyone's worn out.
Yeah.
The thing that I learned last week from the Near-Surface-Chile one, that by the end of the day, you're pretty tired.
Yep.
But this time we wanted to, try and get a lot of information out there to stir people up in the first place and have these slightly different perspectives. And I think we achieved that goal for sure. I'd probably like to, I was chatting with Gustavo a little bit like this, sort of now start having potentially like monthly meetings. I mean, not long ones like this, but have monthly sort of a chat and catch up for like an hour or so every month fairly regularly, just at least to see what people are doing, find out where people are at and how that applies to the Tachocline sort of stuff. So
what do you envisage as the cycle for full day workshops like this? Once a year or what?
Yeah, that's a good question. And Todd's not here. We could ask him, but I mean, for me, I think there's going to be a once a year all COFFIES type thing with everything going on, with all bits of it, trying to bring everybody rather than just concentrating on one theme, trying to bring themes together. And I think there will be at least one of these per year. I think so. Maybe it's a sort of a twice a year for the whole of COFFIES type of thing.
Yeah, stagger them.
Yeah, well, they're talking about having a sort of kickoff meeting in January, which already to me feels like a little soon.
Yeah.
And we already did a sort of an add-on to the test meeting, which was only in August. So I feel like we're doing quite a lot in a row right now for the people that have been to all those things. But I think, not necessarily all of those things are going to happen every year. But I think one more specific by theme and one more general by the whole of COFFIES is probably going to be fairly reasonable. So yeah, we'd love everyone to come to all those things. Anyway, so I think, people are getting tired. I don't think want to force people to discuss when they're not really have anything to say. So thanks very much for everyone's participation today. It was a pretty good turnout, and I think we got some things to digest. So that's it for now, and we'll let you know what's happening in the near future.
Yeah, there are a lot of comments in the board, so we have to review that. Yeah, we got around to a lot of the ones that are in the boards as well. So that did generate some discussion already. So I think that's good. But we happen to go back to and say, look at once again. Okay. All right.
Thank you.
Thanks very much. Thank you, co-hosts.
Thanks for organizing everything.
So long.
Bye-bye.